tutorial, I'm going to give you a mathematical proof of Newton's third law is equal to conservation of momentum. I'm going to first start writing Newton's third law and also going to write the equation of conservation of momentum. And we're going to give you lots of examples so that by end of this lesson, you're going to be not only understanding that Newton's third law is equal to conservation of momentum, but also you're going to understand that 3 types or 4 types of collisions. So you're going to be talking about elastic collision, perfectly elastic collision, elastic collision, inelastic collision, and perfectly inelastic collision. So let's get started with writing Newton's third law. So Newton and then the conservation of momentum law, conservation of momentum equation. The Newton's third law is FAB is equal to negative FBA. What does that mean? The force acting on object A due to B is equal in magnitude of force acting on B due to A, but opposite in direction. And this one also look the same. Momentum before is equal to momentum after m1 v1 plus m2 v2 is equal to m1 v1 plus m2 v2. Now let me give you an example to make a connection between these two. All right, so let's consider this problem before and after. So there's a gun and there's a bullet, right? And then after you pull the trigger, what happened? After you pull the trigger, the gun goes one direction and the bullet goes to the other direction. So the bullet gonna go to this direction, of course. This is the bullet and it's gonna go this direction. And this is the gun gonna go this direction, right? This is called recoil velocity, right? Because the gun gonna go one, so we are trying to find the recoil velocity of the gun. So this this before you can call it A, and this after you can call it B, or you can call G for gun and B for bullet. All right, let's see how Newton's law look like over here. So first we're gonna use M1 v1 plus m2 v2 is equal to m1 v1 plus m2 v2, right? Okay, before what happened, before this gun is at rest. All right, make sure you put prime. Bullet is also at rest. All right, after the gun is not at rest, so the gun has some mass 5 kg and gun has some velocity, we need to find that. And bullet has some mass of the bullet is, I don't know, 0.002 meter kilogram, and bullet has some velocity. Velocity of the bullet is, let's say, 800 meter per second. Bullet really has a velocity. Bullet moves faster than car for sure. Okay, so now here's what we have. The gun is at rest before, the bullet is at rest before, the gun is moving because the bullet is moving. Why the gun is moving? Well, because the bullet, this is because Newton's third law, right? Why the gun is moving? Because Newton's third law. So I'm gonna write the gun and bullet, and then the bullet, and then the gun, right? Okay, so you understand, right? The gun is moving is because bullet is moving, right? Bullet goes this direction, that's why gun is going this direction. This is just Newton's third law. All right, excellent. So I'm going to bring this guy to this side. So m1 v1 prime is equal to m2 v2 prime. Don't forget negative because you bring it to the other side. Now multiply both sides by negative, so negative going to go this way. All right. So what are you trying to find? You're trying to find b1 prime, which is negative m2 v2 prime over, of course, m1. So v1 prime is equal to m2 is how much? M2 is a very small point, 0.002 times you have the velocity of the bullet 800. The mass of the gun is how much? Mass of the gun is 5, right? Okay, good. Now, negative 0.332 meter per second, right? So the velocity of the gun moves this direction with this, all right? So this is the gun moves this direction with how much? 0.32 meter per second, because the bullet is moving this direction, of course, with how much? 800 meter per second. The bullet is moving this, if the bullet moving this direction is 0 meter per second, then gun is not moving. So gun is moving because bullet is moving, right? So you see Newton's third law, connection of Newton's third law. I'm also now going to show you that this is also connected with the momentum by showing that the momentum is conserved. Alright, momentum is conserved no matter what type of collision it is, right? Okay, so M1 is 0, B1 is 0, M2, well, M1 is now 0, M1 is 5, V1 is 0, because the gun at rest. M2 is 0.002, V2 is 0 because the bullet is at rest. Gun, bullet, both of them is rest, so both of them velocity is 0. Not rocket science. Mass 1, which is 5 kilogram. The velocity, you got the velocity, right? The velocity of the gun is a negative 0.32 plus mass of the bullet is 0.002, and velocity of the bullet, I forgot to put prime, and don't forget to put 800. So this is negative 1.6, negative 0.16, yeah, 0.16, and this is this is negative 1.6, this is positive 1.6, and so therefore 0, right? So what do you get? You get so you get 0. 5 times 0 is 0, plus 0 is equal to, this is negative 1.6, this is positive 1.6. So 0 plus 0 is 0, this plus this is 0. So yeah, momentum is conserved. So you see that Newton's third law over here, the bullet goes this direction and gun goes this direction. This is Newton's third law, right? Equal in magnitude, opposite in direction, all right? This is momentum, okay? We see that the momentum is conserved in this type of, all type of collision momentum is conserved. That's what I'm going to show you right now. So speaking of momentum conservation of momentum, let's first start with this. Let's first define the elastic and inelastic object, right? So this is so elastic and inelastic Okay, so in elastic object, you can stretch, you can compress, right? You can stretch, you can compress. In elastic object, like for example, like this spring, right? You can stretch it, right? Or you can compress it, right? Or you can stretch it, or you can compress it. Stretch it, compress it. Stretch it, compress it. It resists to, this object resists to deform, right? Resists to change its shape, right? So when, for example, I apply the force this way, right? Is want to go back, right? So F is equal to negative kx. So the restoring force is this direction, okay? So spring is a good example of what? Spring is a good example of elastic spring. In elastic, you cannot stretch or you cannot compress it. Stretch, compress. Well, no, you cannot stretch it, you cannot compress it. For example, glass. Glass is a good example of the object not so elastic. Okay, so you get it. Now we're going to try to find other differences of elastic and inelastic. So we're going to say we're going to add two more things. We're going to say perfect elastic, and perfect inelastic. And we're going to write the conservation of momentum, and conservation of energy, conservation of kinetic energy, right? In a perfect elastic collision, conservation of momentum, yes. Elastic collision, yes. In elastic collision, the momentum is conserved. Perfect inelastic, momentum is conserved. So what do we learn? All type of collision, momentum is conserved. Momentum conserved regardless the type of collision. Now let's see kinetic energy. Yeah, kinetic energy conserved, kinetic energy conserved, kinetic energy not conserved, kinetic energy never conserved, right? In this case, I believe you can restore, you can get about the maximum of about 37 or less than 40 kinetic energy conserved. And here I think 20% or less kinetic energy being conserved, more or less. Okay, I'm going to give you now equations, and then of course but equation has to make sense. So to help you understand those equations, I'm going to construct some scenarios, right? So let's start with here. This is inelastic or perfect inelastic collision, right? So you have a ball A and ball B. Let's separate them, and they move toward each other, right? So momentum before and momentum after would be when they collide, they stick together, right? A and B, and they move to the same direction, either this direction or this direction, right? Okay, so that's all about the perfect inelastic collision. And then what is the evidence? They stick together. Okay, now inelastic collision. Alright, so ball A and ball B, they move to each other, right? And then after collision, this is before, momentum before, momentum after would be, and then they changes the direction. A changes the direction and B also changes the direction, right? And then now we're going to get to see the perfect elastic collision. So perfect inelastic, this is inelastic. So perfect elastic collision. I don't have to write collision because you already know we are talking about the collision. Let's write momentum before and write momentum after. Alright, so the ball A is moving, ball B at rest, right? Ball B at rest. They both are the mass 1 and mass 2. Mass 1 has to be equal to mass 2. Alright, so make it same size. Alright, after mass 1 it stops and mass 2 start moving, right? Okay. Alright, now what happened during the collision? All energy transferred to the ball B, right? In this case, kinetic energy. What about momentum? What about kinetic energy? What about momentum? What about kinetic energy? What about momentum? What about kinetic energy? As I told you, momentum hold, momentum conserve, right? All type of collision, momentum conserve. Kinetic energy never conserve, kinetic energy never conserve. Yeah, kinetic energy conserve. Okay, good. Now let's give you the equation for this one. Equation for this one is pretty simple. V2 prime or just V prime, right? Because I just want to write it in a full form. m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime, right? This one is this, and I want to make a correction to this one because that's wrong. V prime m1 plus m2. Now it makes sense with the diagram. It has to make sense with the diagram. One velocity, because they become one body after the collision, right? So the formula finally is, of course, m1 plus m2, m1 v1 plus m2 v2. Okay. All right. Inelastic collision. What are we going to do with inelastic collision? Let's see. We gonna write the equation, right? m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime, right? Okay. In this case, we're gonna just write m1 v1 plus m2 v. Oh wow, this one would be much easy. m1, I'm gonna write it over here. m1 v1 is equal to m2 v2, right? That's it. So this is the equation for perfectly elastic. This is the equation for inelastic. I'm gonna write this equation over here. m1 v1 plus m2 v2 is equal to m1 v1 plus m2 v2 prime. All right, and this is for this one, perfect inelastic. So I'm going to write this version, or maybe this version, doesn't matter. So v prime, maybe I write m1 v1 plus m2 v2 is equal to v prime m1 plus m2, right? Okay, so I'm going to erase this, and now I'm going to give you an example on all three. So let's see how much you understand this. Okay, so now start with, and then of course I'm going to show you then whether kinetic energy conserved and whether the momentum conserved. So let's start with this one, right? Start with this one, and then we're gonna give you the other one. So I'm gonna erase it to make the room. So first, three column proof. So first I'm gonna show you the problem, and then I'm gonna check kinetic whether momentum conserved, and then I'm gonna check whether kinetic energy conserved. What is the problem? Say ball A moves with velocity 2 meters per second. Collide with ball B. All right, this is before, momentum before, and this is momentum after. Ball A come to stop because after the collision it gives all velocity to ball B, and that's what we're going to find. By the way, in this case, the ball A mass 1 is equal to mass 2. Mass of ball A has to be equal to mass of ball B because it's perfectly elastic collision. So again, you write m1 v1 this equation. So you're gonna write m1 v1 is equal to m2 v2 prime, right? Is equal to m2 v2 prime. So v2 prime is equal to m1 v1 over m2. So v2 prime is equal to m1 is of course 5, v1 is of course 2, 5, right? So v2 prime is equal to 2 meters per second. All right. So it's not a surprise that you got 2 meters per second, because you know all along, because potential, because no momentum lost, no kinetic energy lost. Good. We're gonna prove that. Have to prove that no momentum lost. So how? m1 v1 is equal to m2 v2 prime. m1 is 5 times 2 is equal to 5 times 2, so 10 kilogram meter per second is equal to 10 kilogram meter per second, right? So now we see that the momentum is conserved, so we're gonna write momentum conserved. All right, now we're gonna check the kinetic energy conserved. Half mv square plus half mv square is equal to half mv square plus half mv square. We have to be careful. 1 1 2 2 1 1 2 2 prime prime. This one is at rest. All right, this one is at rest. This one is at rest. This one is at rest. Okay. Half cancel. So m1 v1 square is equal to m2 v2 prime squared. m1 is 5, v1 is 2 squared, m2 is 5, v2 is 2 squared, right? So 4 times 5, 20 joules is equal to 20 joules. So the kinetic energy also conserved, right? Now we have to prove the next one. Okay. Remember what inelastic is? Let's draw the diagram again. Ball A moves toward ball B before, after ball A moves now this direction and ball B moves to this direction, and this is inelastic, not perfect inelastic because they bounce off. That's the evidence, key evidence. That's what it means, bounce off. Okay, now we want to see what would be the velocity, but let's give some value. 0.5 kilogram, 0.3 kilogram, 2 meter per second, 4 meter per second, 0.5 kilogram. Find the velocity of 1.3 kilogram, 2 meter per second. What are we trying to find? Make sure we understand this. We are trying to find this. All right. So again, m1 v1 is plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime, right? Okay. So m1 is 0.5 times 2 plus m2 is 0.3 times 4, negative 4. Make sure you understand why it is negative, because look, is moving to the west, and you have to understand that the momentum is a vector quantity. m1 is 0.5, v1 is, we are trying to find, m2 is 0.3, v2 is 2. All right, so this is 1 minus 1.2 is equal to 0.5 v1 prime plus 0.6. So 0.5 v1 prime is equal to 0.8. So v1 prime is equal to 5 goes to 8 one times, and then 3, and then 5 goes to 36 times. So 1.6 meter per second, and that's how fast this one moving, but this has to be negative, right? So this one is negative 0.2. All right, so this one is negative, so this is negative. So 1.6 meter per second, of course, is negative. Okay, now we have to check whether the kinetic energy, the momentum hold, right? So momentum, check the momentum. So momentum is m1 v1 plus m2 v2 is equal to m1 v1 plus m2 v2, right? So m1 is 0.5 times, of course, 2, m2 is 0.3, of course, negative 4. M1 is 0.5 times negative 1.6 plus M2 is 0.3, velocity is 2. Alright, so this is 1, this is negative 1.2 is equal to, this is negative 0.8, this is 0.6. So this is negative 0.2, this is negative 0.2. Yeah, momentum conserved, as we see. Kinetic energy, half mv square plus half mv square is equal to half mv square plus half mv square. 1 1 2 2 1 1 2 2 prime prime. Half cancel. M1 V1 squared plus M2 V2 squared. M1 V1 prime squared plus M2 V2 prime squared. M1 is 0.3, 0.5, V1 is 2 squared plus M2 is 0.3, V2 is negative 4 squared, M1 is 0.5, V1 is negative 1.6, M2 is 0.3, V2 is 2 squared. So 4 times 0.5 so this is 2 and this is 16 times 3 4.8, so it's 2.48. Right, so 6.8 and 2.48. Alright, so you conserve 37%. So how much conservation of energy? 37% conservation of energy, and remaining energy lost. So as you see that conservation of energy does not hold, because you lose 37, you conserve 37% of the energy, right? You conserve 37% on energy, but remaining energy lost. Okay. All right, in this case, yeah, momentum conserved, but the conservation of energy doesn't hold. Conservation of, you do not conserve the energy, because some energy lost, some energy, yeah, conserved. What percent of the energy conserved? 37% of energy conserved. Okay, and now we're going to do the last one. Okay, so let's do the last one, the perfectly inelastic collision. So perfectly inelastic collision, right? So ball A moves to ball B, right? This is a momentum before, this is momentum after, right? Momentum after ball A and ball B, they move in the same direction, probably this way. But the math will probably give us more information. Let's say this is 0.5, this is 0.3 kilogram, and this is together, right? So we want to find the velocity final. Let's give some velocity meter per second, 2 meter per second. Okay, so this is the information we know. What are we gonna do now? Momentum before is equal to momentum after, so m1 v1 plus m2 v2 is equal to v prime m1 plus m2, right? M1 is 0.5 times 4.3 times negative 2 is equal to b prime 0.8, right? So 2 minus 0.6, b prime 0.8, b prime is 1.75 meter per second, 1.75. Good. I'm going to see whether the momentum conserved, m1 v1 plus m2 v2 equal to v prime m1 plus m2, right? Okay, or you can directly write m1 v1 prime plus m2 v2 prime, doesn't really matter. M1 is 0.5 times 4 plus 0.3 times negative 2 is equal to 0.5 times 1.75 plus 0.3 times 1.75. So this is 2 minus 0.6 is equal to 1.4. So 1.4 is equal to 1.4. So kilogram meter per second, right? Kilogram meter per second, right? So yeah, momentum conserved. Now you're going to see the kinetic energy conserved. We know that kinetic energy is never conserved, but probably 27% or maybe 26% or a little bit more than 20% will conserve. Let's see. Half mv squared plus half mv squared is equal to half mv squared plus half mv squared, right? 1 1 2 2 1 1 2 2 prime prime, half 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 cancel. m1 is 0.5, v1 is of course 4 squared plus m2 is 0.3, v2 is negative 2 squared, m1 is 0.5, v1 is 1.75 squared plus m2 is 0.5 3 1.75 squared 2, and this is 2.45 divided by 9.2, 27% conserved. All right, so most of the energy lost. So the momentum is conserved, but kinetic energy not conserved. All right, only 27% conserved, but most of the energy never conserved. So today we made a connection between Newton's third law and conservation of momentum. We talked about 3 types of collision: elastic, inelastic, and far-flung inelastic. And we also talked about that elastic, momentum, and kinetic energy conserved, inelastic and far-flung inelastic, momentum conserved, but kinetic energy never conserved.